Thanks. So my name is Paul, and today I'd like to present our work, BFF, in verifying the functional correctness of Bitfield manipulating programs. This is joint work with Michael, Rudolph, Derek, and Depark in Max Planck Institute for Software Systems. So in system programming, bit operations are used in many different ways, such as to perform arithmetic computation more efficiently, to realize some cryptography algorithms, including encryption, decryption, and also bit field manipulation to manipulate the bit fields that are packed into integers or bit vectors, such as network packet headers and page table entries. The last usage, bit field manipulation, is what we are going to focus in this work. And to give you some more concrete understanding of what Bitfield manipulation looks like, I'll show you an example. So in this figure, it shows the structure of an 8-bit integer that encodes 4 pieces of metadata of a file header, namely the read, write, and execute permission flags, each takes 1 bit, and followed by 4 bits that encodes the owner of the file. The highest bit is left unused. Then I show you this C function is writable. As the name suggests, it will test if an input header is writable or not. So more specifically, we are doing bit field manipulation in this function, that is to extract the value of the write field from the input header. The developer realizes this functionality by applying a bitwise AND operation between the input header and a bit mask where only the bit that represents the write field is specified. So such bit field manipulation is everywhere in system programming, such as in Linux kernel, we find many components, their implementations are relying on bit field manipulation. So towards the ultimate goal to verify those system software such as Linux kernel, it is a must-have step to reason about the correctness of the bit field manipulation. And this is the problem we are going to address in this work. And more specifically, we want to achieve 2 goals for our verification simultaneously. Namely, we want to achieve a kind of foundational and automated verification. So first of all, foundational means that the proofs for the correctness of the programs are constructed in a way such that they are machine checkable in general purpose proof of systems such as COC. We find this is particularly important for system software because safety is very critical, and this kind of approach so far gives us the strongest guarantees on the verified programs. At the same time, we also want a kind of automated verification, which means the proofs are mostly inferred automatically instead of written by the users. We think this is also important for bit field manipulation because in general, the bitwise reasoning is low level and time consuming. So we want to save human effort and also which increases the practicality of our approach. So how do we achieve these 2 goals at the same time? So we start with RefinedC, a framework that already supports some sort of automated and foundational verification for C code. So this framework is first of all foundational because it's formulated in COC and Iris. And also it builds some automation support, let's say for C language features and some commonly seen site conditions generated by the verifier can also be automatically discharged. But RefinedC lacks support for bit field manipulation. And this is what we want to do. We want to, on top of RefinedC, we want to build support for bit field manipulation. So before showing how we can do this in RefinedC, I'll first show you a very important concept in RefinedC, as its name suggests, is its refinement type system. So in RefinedC, a refinement type can be polymorphic. That is, you can take some type arguments, and the refinement of the type on the left-hand side, the R, is a refinement that can be a COC term with compatible types. So I'll show you some of the built-in types in RefinedC. For example, the integer type is actually a singleton type whose only inhabitant is an integer value n of the integer size alpha. And likewise, the Boolean type is a singleton type that represents a Boolean value b. And the ownership type, following the Rust style, is a singleton set of location L, which this location points to and owns some value v that has type tau, which is the type argument of the ownership type. All these types defined in RefinedC are defined in a semantic way. In particular, they are using iris separation logic to give the meaning of the type judgment. And following this kind of semantic typing, the typing rules are actually propositions. So we also need to reason about the soundness of the typing rules. And the soundness have been proven in cork and iris. As you can see here, RefinedC already supports integer type, and also some typing rules that allows us to type check the bitwise operations used. So you could come up with a naive approach that we can simply reuse these typing rules to type check the bitwise operations in our problem. And then the main problem would be how to automatically discharge the proof obligations generated by the type checker. And once you realize these obligations are mostly using bit vector theory, then it could be you may resort to SMT solvers that already support some bit vector decision procedure. And then you may wonder, can we just do, let's say, RefinedC plus SMT solver? The answer is unfortunately not, because we find there are two drawbacks of this kind of naive approach. The first thing is that SMT solvers are not foundational. Namely, some of the previous work has shown the solvers have bugs. And even if we can come up with an approach that we can check the correctness of the solver results in RefinedC, so to make them foundational, this kind of approach using the bit vector theory is still not ideal because it's too big a hammer for verifying our problem to verify the bit field manipulation. It's just like, when you want to try some new language feature, let's say in Scala, then you don't have to, let's say, create a SBT project with a GitHub action for building a project. But you can simply open your repo, you do some typing, then the compiler does some typing, right? And then you solve the problem. You don't need to adapt a more complicated approach. And this is the same to our problem. The general bit vector theory is too complicated, but to solve our bit field manipulation, only a fragment of it is needed. So we're taking a different approach in this work, and our key observations are the following. We realize that in bit field manipulation programs, first, the bit vectors, they have structures. And we call them structured bit vectors to distinguish them with the raw bit vectors that does not have any internal structure. And second, this structure information is known by the developers. And we should definitely let developers tell us, and we make use of this information. And finally, we find that the valid bit field manipulations, they only use bitwise operations in restricted ways. They are not using it in a general or generic ways. So following these key observations, we propose a new approach that is based on the following ideas. First, we extend RefinedC's type system with new types that can represent the structured bit vectors. And the most important thing here is that we want to encode their structure information. And second, we extended RefinedC's front end so that we can have some user annotations that the developers can describe the structure of bit vectors. And finally, to type check these the bitwise operations in bit field manipulation programs, the typing rules are only restricted to the common bit field manipulation patterns. We are not dealing with the general typing rules for any kind of bitwise operator. So putting these ideas together on top of RefinedC, we present BFF, a new framework that aims to verify the functional correctness for bit field manipulation. And since we are now just dealing with a fragment of the general bit vector theory, we can achieve a kind of foundational and automated verification. Now, in the next part of talk, I'd like to show you by this example how BFF can verify the functional correctness of this function. And we know that in doing verification, the very first step is you need to provide specification. And in BFF, for bit field manipulation programs, our specification is divided into two parts. The first part is the structure, which is the very important information of the usage of bit vectors. And in our front end, we introduce a new annotation, namely the RC bitfields annotations, as you can see here. Specifically, the user has to specify the name of these new types of structured bit vectors, the integer size of the underlying bit vector, and the the names and positions of the logical fields in these types of SPV. Then our frontend will automatically from this annotation generate a cork record that represents these types of SPV in a structured way. And also we generate some other auxiliary definitions and lemmas that are useful in verification. Now with this generated record file info in hand, the user is now ready to provide the second part of the specification, which is the specification, which is the functional correctness of a program. We provide these annotations using RefinedC standard annotations. And for this particular function, we need 3 lines of annotations. And intuitively, they describe the following specification. For all file info H, this function returns a Boolean value, which is the value of the right field of H. Now let's look into these annotations line by line. The first line, the RC parameter clause, we use it to declare some universal quantified variables that are useful later to describe your specification. The second line, the RC args clause, is used to assign refinement types to input arguments of the C function. And here, to make use of the generated record, which contains some sort of structure information, we introduce a new refinement type, the bitfield type in RefinedC that can encode the structured bit vectors. And this refinement type is parameterized by a record type, big R. And particularly this R is generated from the user annotation. And the refinement of this type is a record term, the small r, that belongs to the type R. Semantically, this refinement type represents an integer value or an integer type whose refinement is the denotation of the record R, which is the integer value of the underlying bit vector that R represents. So with this new bit field type, the user can have a rather simple way to bind the input arguments with a structured data. Namely, here we use the h@bitfield file info type to bind the input argument header. And intuitively, this allows us, this introduces some sort of equation that the value of the header is equal to the denotation of h. And the third line, the RC returns clause is used to assign refinement type to the return value. And here, according to our specification, we expect this function to return the right field of h. So we simply use a cork term h.right as the refinement of the Boolean type. So far, the user's job is done, and now BFF takes over the verification. For this example, these 3 lines of annotations is sufficient for automatically discharge everything for this example. So now let's move on to the verification side. That is how BFF can internally verify the functional correctness according to the user specification. And we know that in RefinedC has a refinement type system, and its verification process is actually doing type checking. So the most important thing for us is how should we type check the bitwise operators used in Bitfield-Manipulation programs. We start with this general template, which is quite usual and similar to other typing rules you have seen that are used to type check the bitwise or arithmetic operators. So here we have a type judgment to type the C expressions. So in the premise, we have for C expression the left-hand side E1. The type is a bitfield type that's refined by R1, and we have and similarly for the right-hand side. Then we want to infer what is the type for the binary expression E1 OPE2, where OP is the bitwise operation we're considering. And the interesting thing about this typing rule are 2 points. The first thing is that since for each kind of Bitfield manipulation, they have some restrictions on how the bitwise operator is used. So we need a placeholder $P. You need to figure out what is the additional restriction for this kind of Bitfield manipulation. And second, the $R is the refinement of the resulting type. Namely, we want to compute a resulting structured bit vector that is consistent with the semantics of doing the bitwise operation OP. So formally, it is to say, well, you want to have you want to compute a resulting SPV R such that its denotation is equivalent to applying the bitwise operation on the denotation of its operands. And also, there is another important thing here is that since we know the structure of the bit vectors, in computing this resulting SPV, we don't want to introduce any more bitwise operations. We want to achieve a kind of computation that can get rid of this bitwise operation at all, so that we can have a rather simple reasoning technique. Now, in the next couple of minutes, I'll show you some instantiations of these typing rules, and they represent two different kinds of bitfield manipulation. The first kind of bitfield manipulation we're looking at is masking bitfields. So for this typing rule, first of all, the additional constraint we required is that at least one hand side of the operator must be a mask. So here we define the mask to be for every field f of this structured bit vector R, its value is either all 0 or all 1. And here the rule only shows the case it only shows the case that the right-hand side is a mask. And second, we need to figure out what should be the resulting SPV according to this kind of masking bitfields operation. And here we introduce the extraction operator that gives you the result of computing the bitwise AND between R1 and R2. But interestingly, we are not defining this extraction operation in a total way, but we define it partially. Because as you can see, the typing rule requires that R2 is a mask. So we can just, and this operation is only applied when this premise is held. So we are actually defining this extraction under the condition that if R2 is a mask. And once you realize this, the definition could be rather simple. Because R2 is a bit mask, we can simply extract from R1 all the bit fields that are specified by R2. And then we can show a lemma that this definition, the extraction operation, is semantically consistent with the usual definition of bitwise AND. Then you should also realize in the definition of this extraction operator, we do not use any bit operations at all. Now I'll show you an example of using this typing rule, which is the C expression, header, and bit1, which we have seen in the example. So this typing rule applies to type check this C expression because the right-hand side, the bit1, is a mask according to our definition. And intuitively, as you can see from this figure, the masking bitfields operator, this kind of bitfield manipulation is actually extracting the value of the right field from the input header. Now let's move on to another kind of bitfield manipulation, namely, and now you may wonder what happens if this premise, R2 is a mask, is violated. So in short, this means that the user is actually doing something wrong. He is not doing some sort of bitfield manipulation, but something else. As you can see in this example, if the user expects to extract the owner fields from header, but this code is doing something wrong because the right-hand side, the gen mask 53, is a bit mask that only specifies the lowest 3 bits in the owner field, but not the entire bit field, which according to our definition, this is not a mask with respect to this file info SPV. So our type checker will reject this program. Now let's move on to another usage of bitfield manipulation, the merging bitfields. In this kind of operation, we require that the bit fields specified in the two operands must be disjoint. And the reason we want that is that if they are not disjoint, there can be some conflicting results in computing the merging. And similarly, to define this merge operation, which gives you the result of computing the bitwise OR between R1 and R2, we still do it in a partial way. We require that under the condition R1 and R2 are disjoint, this merge operation is definable. And since we know their bit fields are disjoint, then we can simply take the union of the specified bit fields from the two input. And since they are disjoint, there cannot be any potential conflicts happen. And again, we can show that this operation is semantically consistent with the bitwise OR operator. Also, no bit operations are required in the definition of the merge operation. And this rule can be applied to, for example, the C expression honor, bitwise OR, perm. And this applies because the honor specifies only the honor field, and the perm specifies two permission flags. So they are disjoint. And as you can see from this figure, the meaning of doing bitwise OR between honor and perm is just to merging the bit fields they have. Using the rules I have just shown you, you can apply it to verify more complicated examples, such as this set value leave BTE function taken from the pKVM page table entry code. And you can find more details in our paper. In addition to the masking and merging bit fields I have shown you, there are more kinds of bit field manipulation we're considering in the paper. And we introduce, again, more typing rules on type checking these operators. We also conducted case studies on 4 code bases, which we extract some bit field manipulation functions from these code bases. And as you can see from this table, most of them are automated. We see there are 3 manual side conditions, which means they have to be proven with manual steps. And the reason why we need that in these side conditions are the bitwise operations in them are actually not doing bit field manipulation, but rather a combination with the arithmetic operation to do some sort of arithmetic computation. And also, the annotations we required are in a reasonable amount. You can find more details about these case studies and the metrics in the paper. And finally, I'd like to mention a minor technical issue that is different from what I have shown you. So this typing rule is what I have shown you to type check the bitwise AND operation on masking bit fields. And this is mostly just a proof of concept. And if you want to directly implement this typing rule in Cork, you will find a problem, which is if you want to compute the masking result between R1 and R2, you have to define some operation that is generic to R. Because since this R is user-defined, we find it really hard to implement in Cork because we didn't know how to compute a record without knowing its structure. So how to fix this technical issue is so the possible approach is that instead of using this generic operation, we can have a more general representation of structured bit vectors that are independent with the user customized types. So our idea is that we want to introduce a new type refined by this kind of representation. So here, the new type, the parameter is what we call a signature. And as you can see from this example, the signature, the sigma file info, is just a list of bit ranges. It does not contain the name of the bit fields. So this is a more general representation of the file info record. And then the refinement of this BF term type is a term of sort sigma. And the simplest case for the term we define in our system is essentially a list of mappings from the bit ranges to their integer values. And you can see it's easier that we can translate a record into this kind of term by simply replacing their field names with the corresponding bit ranges. And since the bit ranges is something that is not depend on the user customized record, we can easily define the operation, namely the merge operations on terms. And finally, since our specification is still using the bitfield refinement type, because that's more high level and structure that the user can understand that easily. So in verification process, we will use this translation rule to desugar any bitfield types into BF term types. And then the actual typing rule we are used in our implementation to verify the masking bit manipulation is the following, which you can see where instead of using the Bitfield record type, the Bitfield refinement type, we're using the BF term refinement type. And the merge operation on term can be defined in a way that does not depend on the user customized type. So now this is definable in Coq. So to conclude, the key insight of this work is that the typical bit field manipulations, they operate on logical and high-level structures of fields that are packed into integers, which we call structured bit vectors. And to make use this part of structure information, we implemented on top of RefinedC some new types for representing structured bit vectors, some typing rules to type check the bitwise operations. They follow the pattern of bit field manipulation. We also prove their soundness according to their semantic typing style. And also we formulated the meta theory of the terms and their operations. If you are interested in more about how this is formulated in Coq and how our case studies are conducted, you can find this artifact, the source, in this link. Thanks for coming, and I'm happy to take any questions.
We have time for one or two questions. I had one question. Can you give some insight on limitations that you found using refinements? Were they sufficient for all of the kinds of problems that you were looking for, or did you find instances where RefinedC was insufficiently expressive to actually verify properties that you thought was interesting?
Oh, you mean some limitations of RefinedC in general, or mostly
for this particular application class?
Yes, I think as I mentioned, like in the beginning, we know bitwise operations, they have different kind of usages. And our work is based on the assumption that you know the bit vectors, they have structures. And I think one obvious limitation is that if the structure is not known, let's say, or they are used in some internal way, or they are used in a more generic way, then it's hard to apply this approach on that problem.
Thank you for the talk. So in the beginning, you said like the bit vector theories in SMT solvers will be too heavy hammer for this. Do you have some kind of examples like why that will be the case? I'm not able to see right away at that.
You mean some examples? I think actually we didn't really, seriously examine why the SMT solvers are, too big a hammer, but an intuition that I know is that, in SMT solvers, if you want to reason about bit vectors, usually we will use encode. We will simply introduce a lot of variables to encode, let's say, a 32-bit integer. You introduce 32-bit Boolean variables. And then you can say, well, this will introduce too much space waste because you have to really reason about each single bit of the integer value. But in this approach, you can say we are not actually dealing with the bit vector bit by bit, but rather field by field. So which you can see there, at least I think conceptually there are some memory saving, and also, we are not reasoning about bit operations, which if you are doing some bit blasting, is actually dealing with some Boolean computations, like doing proof theorems about, the Boolean combinations, which is the set problem. And in this work, we get rid of that. We are not dealing with the set problem, which is also, it's a hard problem in general.
Thank you.
Thank you for that. Let's thank the speaker.
Thanks.